Welcome back. Let's talk refracto-vibrometry. It's not supposed to be a deep dive, but just a dive into this application. And we have put some resources in the notes section of this YouTube video. Two slides. What is refracto-vibrometry? And very simply put, it's a way to visualize sound using vibrometry. So if you have a ultrasonic transducer or even something in the audible frequency range that you want to see how is the sound propagation or wave propagation as it generates in a medium. It's a qualitative way to do a quick feedback on the characteristics of your ultrasound transducer. I guess where it really stands out is in these higher frequencies, which is just way beyond the capabilities of a microphone and just a much easier setup. On the right here, you see an ultrasound transducer, and this is an image that you would get as a result of a refracto-vibrometry test. The beauty of it is, of course, you can use hydrophones for underwater, but now you can use one sensor for either in air or through water or through any kind of, optically transparent gaseous medium as well. What is it and how does it work? So, first of all, let's just go with this is the source that we are trying to characterize. This is what we want to characterize. The setup looks like following. Perpendicular to the source, we'll put a vibrometer, a rigid plate, zero velocity, no movement, absolutely no movement on the other side. And then when we start the source, basically start the excitation on your source, whether it's a speaker or an ultrasound transducer, whatever it may be, through a medium, air, water, whatever. This the waves in this medium cause very minute density fluctuations. These very minute density fluctuations cause slight changes in refractive index. So now when we measure with the vibrometer on this rigid plate, which we should just see zero velocity, no movement at all, you would see actually some motion. And this motion appears because of this change in refractive index. So this would be like a time domain measurement. So now this is a 1-point measurement. So if you look at the spectrum the time domain data, you would see these fluctuations that you can then, of course, FFT as well. Now, if you take it one step further and measure at multiple locations, on your plate, then you get the entire sort of the radiation pattern or the wave propagation pattern in this medium, which is invisible and inaudible in many cases, but it kind of makes it visible using this particular technology. And as you can imagine, refracto comes from the fact that it's all about this change in refractive index that combined with vibrometry, now we have refracto-vibrometry. Who cares for this? So what are some of the applications? So kind of put a list on the left with some pictures. So anywhere where you want to characterize what is the radiation pattern, how is it affected? Is it uniform? It's non-uniform? When it comes across some impediment, how does it react? What is the reflection characteristics? So like proximity sensors, the parking sensors as you're backing up. And I've done this before without it, and I've had some minor fender benders without the warning parking sensor. Or there's also parametric speakers. So speakers, some people also call this like a sound laser, where basically it's a focused sound type array of speakers. So that's the top right application. Some levitation examples as well, acoustic levitation, medical ultrasound, where you have an array of transducers and you want to make sure that there is no leakage, there is no crosstalk, there is no sort of aliasing effect. So these things can be quantified, qualified using refracto-vibrometry. Mid-air haptics is also based on an array of transducers transmitting at a certain frequency with a certain amplitude. So to be able to calibrate mid-air haptics type devices is also one of the newer applications. And we got a few more here. So hopefully this gives you a glimpse into this fascinating application of vibrometry. We are here if you have any other questions, and we put some resources in the notes, but reach out if we can help. Thank you very much. Until next time.